Hi Quadrature fans! It's COVID-19 season and today we're going to cover y equals x to the fourth. We will prove that C4 is 4 and K4 is 1/5. Got it! Whoa, keep it going!
Oh, I thought you told me to stop.
Okay, let's roll it. As you can see, whoa, it's getting hot over here. Oh man. Oh, what we're doing, y equals x to the fourth, which will take us to y, well that equals a plus t to the fourth, right? Well, obviously we need to draw our t-axis. T-axis is right here. T-axis, 0 minus a plus a. See how they're related? Good. So we see that using binomial expansion, you get 1 a to the fourth plus 4 a third t plus 6 a squared t squared plus 4 a third t plus 1 t to the fourth. So that we have, well, if we plot it, there's our plots. Oh, I better make it smaller. Whee. This starts at 0 to a on the t-axis. And this would be our, basically, you plug in t equals a, you get a to the fourth. You plug in t equals 0, you get 0, right? That's what this is. Then you get also t to the third. Oh, what am I doing? Obviously, I'm blowing it. This a has to decrease, t has to increase. Okay, I think I got it right. So we've got, here's the t to the third, and there's 4 of them. So we got to make that a little bit bigger. And again, this would be 3 a to the fourth. No, 4 a to the fourth. You plug in t equals a, you get a times a to the third times 4. 4 a to the fourth. So we got this one, this one. What else we got? 6 a squared t squared. Plug in t equals a and you get, you guessed it, that's our quadratic. Something like this. Alright, 0, 6, a to the fourth. That's our quadratic. Here's our linear term, 4a third t. You plug in t equals a, you get 4. And that's just linear, right? 4 a to the fourth, and then the last one is our constant, a to the fourth. So that's how they're stacked. And when you put all these together, well, you get a to the fourth, 4a to the fourth, 6a to the fourth, 4a to the fourth, a to the fourth. You notice that this, well, now I gotta draw them, don't I? Whee! And then I gotta draw that one. And then there's one. It's gonna be really impossible to draw, but I imagine that I did it. It's a region in there. So I basically have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. 1, 2, 3, 4, 5. Okay. And then there's one area here. And notice this area and this area are really the same. And it's also the same as this little wedge here. Okay, so we got it set up for area and for slope. And for slopes, we will be looking at the contributions at t equals a, right, of each of these 5 functions. So you can see this one is 0, this is the linear, quadratic, cubic, and fourth power. And there's a slope that each of these contributes. So if we do the slope first, let's do the slope now. There's no preference whether you do area or slope. Slopes. The total slope for this function at x equals 2a is rise over run. That's this slope of the diagonal times our unknown c4. We're going to try to prove that it's 4. We don't know that yet. In k4 we're going to try to prove that it's 1/5. We don't know that yet, so we're going to solve for it. So here we go. C4, 16, a to the fourth divided by a, 2a, excuse me, rise over run, that gives you this slope, times our magic factor we're trying to find, C4, and that equals the individual areas. This one, the constant is a 0 plus the linear, well, it's 1 times 4 a to the fourth over a. So you can see it's 4a to the third plus the quadratic is 2 times, because we know the C2, right? That's C2 times, well, what is that? Well, that's this diagonal here. And this is 0 to a. So it's 6a to the fourth. 6a to the fourth divided by a. Plus, I have to wipe this down. Now the cubic. Well, cubic, we know that it's 3. That's a C3. We already know that. Times the diagonal here, what is that? 4a to the fourth divided by a. And finally, this term, the fourth power plus C4, our unknown, times a to the fourth divided by a. Okay. And you can see the a to the fourth over a, that simply vanishes. And so we can collect our terms and we get, catch myself. This is 16 divided by 2. I forgot to see, there's a 2, right? It's 2a on the bottom. It's so small, I should make it bigger. 2a. Well, that's 8. And then this is 4, 12, 12, and this is 1c4. So, off to the side, basically we have 7c4 equals 24 plus 4, 28. Well, 28 is 7 times 4. Well, guess what? C4 is equal to 4. We got it right off the bat. All right. Pretty simple, huh? Okay, great. But let's do one more thing, and that is normalize this equation by C4. And why is that? Well, you'll see a pretty pattern, which we already seen in our previous videos. So divided by C4, it's 8 equals, see what I'm doing? I'm just dividing everything by the same factor. Basically, that's called normalization. 1 and 12, this would be 3, 3, 1. And look what it gives us. It gives us 1, 3, 3, 1. 1, 3, 3, 1. Oh, I made another mistake. Good. Okay. 1, 3, 3, 1. What that says is that the relative slopes, basically we're normalizing everything to this case here, the linear case. This is 1 to 3 to 3 to 1. And they add up in such a way that they give us the right slope. So that's kind of nice, you know, that's a lovely ratio. And you can see that the ratio of the function itself comes 1 to 4 to 6 to 4 to 1. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. So that's slope. Now we're going to do area. What's the area? Well, that's the area of this big wedge. And that's basically this box, height times base, or base times height, times K4. K4 is what we're trying to solve. K4 times 16a to the 4 times 2a. Alright, that equals, that big wedge is equal to the area of these 5 areas. This area, the little one, 0 to a on the x-axis, plus constant, linear, quadratic, cubic, and finally 4th power here. So let's add them up. This area here, that would be, that's K4, that's our unknown, times base times height. Yeah, a times a to the 4th, or a to the 4th times a, that's the same thing, plus the linear term, is this one, comes from over here. Well, that's just 1 times base times height, a times a to the 4th. Pretty simple. Plus, now our linear term, well, that's 1/2. Our k factor for linear term is 1/2 from basic geometry, right? That's a k factor. Times a times 4 a to the 4th plus, now we're doing our cubic, this one, Well, that we know already. 1/3. 1/3. That's our K2 factor, right? This is our K1 factor, and this is our K0 factor. So 1/3, that's our K2 times A times 6A to the 4th. 6A to the 4th plus our cubic. Well, cubic we already know it's 1/4 times base times 4A to the 4th, right? This is our K3 factor right here. Pretty simple. Plus, I'm running out of room, our K4 times A to the 4th. And you notice that the A times A to the 4th on all of these will simply cancel out and it's gone. So we collect, and what do we have? We have 32 K4 equals K4 plus 1 plus 2 plus 2 plus 1 plus K4. One equation, one unknown. You can solve it. So the listener can pause the video now and solve it. Okay, welcome back. Hope you paused the video. So we're going to solve this 32, and there's 2 K4, so that means, oh, what do we have? 30 K4, right? 30 K4 equals, well, that's 4, 6. Okay, 6. Well, 30 is really 5 times 6, and look, the 6 will cancel out, you'll have a 1. So the whole thing is K4 is 1/5. 1/5, not 1/4. And that's expected, and that's even something that Cavalieri found himself. So there you have it. One equation, one unknown. K4 is 1/5. That's that's okay. Let's do one more thing. Normalize by K4 just to see the relative areas. And everything is normalized to the smallest area, that being right here, this, as well as this tiny little thing. So let's do that. We get 32 equals 1 plus 1 divided 1, 5 plus 10 plus 10 plus 5 plus 1. That's the relative weight of these areas. 1 to 5 to 10 to 10 to 5 to 1. And now look at our Pascal's triangle. 1, 5, 10, 10, 5, 1. Look at the lovely ratio. This is the, I call that the theorem of quadrature proportions. Notice that the area, it raises by 1 power. And the ratios, the relative ratios, they are also governed by the binomial expansion. And they come 1, 5, 10, 10, 5, 1. The function itself comes as 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. The slope comes as 1, 3, 3, 1, which we just saw earlier. So you see these lovely ratios, and that's all working great. So that's it. So remember, before there was calculus, there was quadrature. That's it.